brief diagram where, how we use Atlas, how we control Atlas. So it comes as a hardware with a bunch of add-ons like the sensor head, different kinds of grippers, as well as other cameras. Every team had at the trials, every team had a field computer which communicated to the robot through the fiber optic tether, and then we had OCUs, operator control units, which had a limitation on the bandwidth. And then we had multiple OCUs actually on our team. So now the basic structure that we use for controlling our Atlas is summarized in this diagram. We do use robot operating system as a tool to get our undergraduates and our students to develop code, but we don't use that to directly communicate to the robot. So there are two key blocks here, which is labeled as field command and field state. They basically handle the communication from the field computer to the robot Atlas, and from the field computer to the OCU. So this helped us a little bit because in our program we teach robot operating systems, so we were able to bring our students up to speed with what needs to be done and how it is done. But then low-level communications were handled by those two software pieces developed by one of our software engineers in the team. We use existing libraries such as MoveIt, RViz, and libviso to carry out the tasks and develop code. Let me briefly tell you how we did, and then I'll go back and explain a little bit more. What was our approach to developing or getting ready for the trials. So on the trials, we scored 11 points, and depending on which day you asked me the question, we came in 7th with 11 points out of 32. We tied, the other stores we tied for the 6th place. We were happy, obviously, because this was top 8. We moved on to the finals. We did receive the best in vehicle task. Our strategy has been we're going to try all these tasks. Because this is what we believe we can do. So immediately when we knew that we were going to participate in the trials, we formed sub-teams around each task. And I remember Dr. Pratt's comment on the trials are your formative assessment, and then finals will be your summative assessment. So we took advantage of knowing the specifics of each task to complete those tasks, and with some level of autonomy that we were able to bring in within 4 months, because we had our robot last year around this time actually, and we were excited. And then at the same time, our Carnegie Mellon side of the team were developing whole body motion control for Atlas. So we were developing low-level controllers so that we can do some of the things that we know that we need to do with this robot. So 7th place in the trials. I'm going to give one example of how we used supervised autonomy, or autonomy where we brought in more automation versus where we used teleoperation in the trials. And I picked the vehicle task. So the idea here is, again, don't try to understand the diagram as this, but the idea here was we used visual odometry to control the throttle for the vehicle. So the user input was to steer the steering wheel, but then the speed of the vehicle was adjusted autonomously as we drove through the course. And this was what we were able to accomplish within the time constraints. Obviously, we were trying to get ready for the trials, and we do believe in the fact that, especially after being part of this community more and more, we do believe that we have to have more autonomy for these robots to be able to accomplish the tasks in real-life situations. So I will show a quick video. This is actually the very first complete test that we ran on our campus. You can tell that it's probably it was close to the trials, maybe end of November or beginning of December in Worcester, Massachusetts. This was our full test before we hit the trials with the vehicle task. Again, we were able to get 1 point, but that was a good point for us. All right. All right. As I mentioned, our approach has been twofold. One was, okay, so let's try to focus on the task so that we can build capabilities to accomplish those in the trials. And at the same time, we know, we had to learn how Atlas work. We had to learn, what to do with it, and Carnegie Mellon had extensive experience with hydraulically actuated robots. At WPI, we did not have a hydraulically actuated robot before we had Atlas. So our CMU team started working on a full-body motion control. It's basically a model-based optimization, model-based optimal control. So at the high-level controller, we develop a set of objectives and constraints for the controller. And then the low-level controller uses inverse kinematics and inverse dynamics to do a mixture of position and torque control to be able to accomplish certain things that we wanted to do on the Atlas. They primarily focused on walking and ladder climbing when they were developing the low-level controller. So these are some of the results or some of the tests that we ran in the garages during the trials. We were able to get almost to the top of the terrain in the last section, and you can see some of the graphs that they generated how they track the left foot, right foot at that CMU. I'll show a quick video, a simulation video, which shows the full-body controller that's currently working on our Atlas, where we can pose constraints. So for example, one of the constraints here is that right hand is fixed, right hand gripper is fixed, and I'm using an interactive marker. The operator is moving the left hand of the arm, and then you can see some of the body motions that we obtain rather than using the split, freeze the legs and do manipulation versus do manipulation and or freeze the arms and do the walking. So this was great because we were able to use this controller at the end. Basically, before the trials, we were able to use this controller on all the tasks that we accomplished. So depending on the time, so what I will do is we have all our videos on YouTube, so I will click on this and hopefully maybe. Wait. Mac, you told it was
That embedded from YouTube?
It was a link to the YouTube. So everything was kind of. Let's try this for a moment. All right. Well, I guess Max can be here too. Sorry about this. Right. I guess we will quickly start. Now continue. So as I said, our approach was twofold. Let's first start building capabilities that we think that we will need in the finals. But then we also did a lot of systems integration in terms of your software and hardware integration to be able to accomplish the task. So for example, when we knew that we were allowed to use grippers that are different than, yes, of course, I have to do this now. So we, for example, used hooks. That's what I was planning to show. We used hooks to perform the ladder task. So maybe I'll just go here. There we go. But I'm not connected. Are you connected here?
You can plug it in, and that'll run up here.
I want to just show this one video where you can see, and then I'll talk about one of the
Thank you.
of course.
There we go.
Yes. Okay. Right, what you see is the official videos that we took for, that are taken by DARPA during our ladder task. So one of the key things that our team members came up was called nudging. In the team, we were calling it nudging. So what it was robot calculates and executes a scripted motion. Let's say for the ladder, we were relying on holding onto the steps to be able to pull the robot up, to be able to climb up. So a robot will bring the hand there, but then it was always up to the operator to be able to adjust this, because we had modeling errors, we had errors, we knew that it may not be the exact location for the hand position. So as soon as the human says, okay, so now I want you to move on, the robot executes and then takes the step and then climbs up. So we were able to get 2 points in the ladder task, which was the best among the Atlas teams. We use this also for walking. So in the walking, the robot plans a step and then waits for adjustments from the user to be able to complete the task. Given that we lost some time, so again, the robot climbed all the way up to the 2-point mark. Actually, we did not plan on what to do when we hit to the top of the ladder, so we basically stopped right there. All right, hopefully we'll go back to this, and it should be all good. So now I want to talk about what we are working on more recently. Okay, and there are no YouTube videos in the rest of the presentation, so it should work. Okay, so one of the things that we suffered, so if you remember the table that I showed you the results, we had 11 points, but we also had 8 interventions, which correspond to faults. Our robot fell more than we hoped that it fell. So, and some of those were due to the collisions that we did not anticipate. Some of those were situations where we did not have time to think about. So what we did since the trials is now we can at least detect self-collisions. As the robot arm starts moving, we can provide this to the operator as feedback, or we can control the robot. Using the full body controller, we can move the robot to avoid those collisions. So this is one added capability now on our robot. We also looked at different kinds of user interface, and this is maybe 2 months old work right now, to provide a better interface between the robot and the user. So you see one of our students, Felipe here, using the Razor Hydra to control the robot. So it was, of course, we didn't know about the bandwidth limitations at that time and so on and so forth. We were just experimenting. So can we control the robot using something more intuitive than the keyboard strokes. Here's what we want to do for the finals. So this somehow gives you a layout of how we would like to tackle some of the manipulation tasks. So since the trials, we restructured our team. We don't have task-specific teams anymore. What we have is a manipulation team, a perception team, an interfaces team, and a lab team, which is basically a bunch of undergrads helping us to maintain the laboratory. And they're doing a great job. So the way that we envision in the finals, and I'm just presenting a specific case for the drill task, right? So the robot initializes or already is in the scene and maps the world, and then passes one set of data back to the operator. And then the operator looks at the scene and sees a drill, and that's what we want to use. So that we can pick a desired area for the robot to travel, to move. And then the robot will autonomously plan the path to the area, will avoid obstacles if there are obstacles, execute the footsteps, and then now it's closer to the drill, it will map the area again and then send that information to the operator. And then the operator can select the drill for a tool, and I'll show you our current implementation of how we do this. Then a bunch of other autonomous behaviors are performed by the robot. So we isolate the drill, locate it, generate feasible grasps. We are not paying too much attention. So what we are doing is we are, for example, modeling the drill as a cylinder, and then around the cylinder we are looking at certain grasps and evaluating those in terms of robot motions. Which ones will cause collisions, which ones are easier to perform, and so on. And then finds a collision-free path, and then sends it back to the operator, and operator approves the plan, and then robot executes the motion, and then now it's time to cut a wall. If the wall is at a different location in the scene, so the robot has to walk. So we repeat that again. The operator says, "Go and cut this wall," and robot moves there autonomously, and then we envision that we will be able to select the points which will conform with the shape of the cut, and then robot will perform the cut and done. So this is our plan. This is how we would like to be able to program our atlas to be able to do that. So for this, we developed it's not really readable here, a manipulation framework. So it takes into account all the capabilities that we are currently building, such as collision avoidance with self or with the environment. So one of the things that you experience, especially if you're grasping a drill which is on a table, you hit the table, for example, right? So we would like to be able to, we would like our robot to understand these situations and avoid those cases. And then eventually a path is generated, and this goes from high level to middle level and low level, and the robot executes those. We also started incorporating more and more perception based on the robot cameras as well as LiDAR. So the way that we envision and currently how we do it is that a scene on the from the robot is seen by the operator. That operator scribbles on the tool, and then the robot knows where it is, and then it can go and pick it up. We recently did a test of this. This is our robot autonomously picking up the drill. After the operator says, here's the drill, we mark it up, and then we want you to pick it up. We love our tools as well. If you notice, we lay our drill in the lab too, just in case we don't drop it and break it. The robots are tethered, were tethered, and they're still tethered, but it was fun to see the video when our students tied the rope around it. So this was with the full body motion controller that's being developed by CMU, and with the added perception and the manipulation framework that we've been working on since the trials. We are also trying to address some of the hard questions. We want to be ready. So we are looking at the vehicle egress. Our vehicle has a lot of scratches already on it, so we started using mats and things like that. So it is hard, but we think that we still think that it's doable, and we are trying to. We are not there yet, but we are, especially on the CMU team. We have a PhD student who is looking at this more and more carefully. We are thinking of getting up after the fall. Again, the ideal situation is not to fall, because we are worried that the hands or the sensor head can be damaged, but we want to have a backup plan. So we started moving. This was the very first time that we laid the robot on the floor as if it fell, and then we were rolling to be able to see what kind of motions we can really get, when the robot is on the ground. Here in this sequence of pictures, one of our team members were rolling the robot, but then since then we started, running some code and trying to roll over. And then we are also working on path planning. So if there are obstacles on the floor that we can avoid, maybe we should avoid them rather than stepping over and over them. So basically, this is an example of where we have now some capabilities about avoiding those obstacles. And just to wrap it up, one of the other things that one of our students worked on is a visual SLAM algorithm while one of our students driving the robot and relying on the stereo vision that's on the robot. Not that this may be directly applicable for the finals, but we want to have, actually we are asking the question, is there value? Can we really do some sort of a visual SLAM in the scene for the finals? So these were our very first results that came out recently. So in summary, we have challenges, I think, like every other team. There are challenges. So there are challenges in terms of modeling errors, the behaviors that we get from the robot. But we have been accomplishing, we have been making continuous progress, especially the whole body control that CMU is developing is what we are using right now. We did really well on the ladder tasks among the Atlas teams, as well as we had the fastest driving in the. We get a lot of visitors from girls and boys and all ages. And then we also take our robot to places. This is Todd Park, Chief Technology Officer of the United States. We were in Washington, D.C. In June, and we briefed him about what Atlas does and what DRC is about. Thank you very much, and sorry about the mishap during the presentation. I'll be happy to take questions.
Any questions?
Yes.
So the ladder task, was that a sort of scripted behaviors, or was that using your full body control and actually planning?
It was using the full body control, and it was using scripts to position the hooks basically on the steps. And as soon as at that point we had the human intervention. We were able to say, okay, so we called it nudging. Through the keyboard strokes, you can move your end effector position to position the hooks better, and then as soon as you click OK, then robot performs another scripted task, and then takes the step.
Okay.
Yes.
So I think you guys, MIT and IHMC, were the ones who sort of did low-level control of the robots. So just given what you know about the different, can you compare and contrast your approach to theirs? What's similar? What's different?
Good question. Should we leave that for the discussion session? Well, I don't know personally, but I think we can identify the pros and cons of it. So our approach is being developed by Carnegie Mellon. I can describe to the best that I can do. It's based on solving a QP problem. We develop constraints, right? So if you, for example, pose your right end effector position as a constraint, and then you use your model for the robot, and then you solve that optimization problem. So I know that the developers of the controller do a lot of adjustments on gains and so on and so forth to make it work for different situations. Does this answer your question? Does this help?
Well, this sounds like a good feed into the discussion topic. If
I believe so.
we get you 3 groups playing off each other for that.
And I think Chris is also online, so I'm sure he'll be able to participate on that.
Why did you get so keen on the driving task?
Why are we
You did such a really good job on the driving task, but everyone else was afraid of doing it.
I don't know. I think it was just, maybe we thought that everyone else was afraid. We'll
There was
just take
there was
a
points
shot
to be
at it,
had.
And again, it took a lot of interventions from the team. So we had to seat the robot very carefully. We had it strapped down very tightly to the vehicle. And after that, it was a manipulation and controlling one of the ankles to push on the gas. And actually, it helped also to have dedicated teams. So we had a dedicated team working on the vehicle task. It was their task to figure it out.
Chris has actually just wrote online. There's a dynamic locomotion workshop tomorrow, and there will be a presentation on the CMU full body control.
Excellent. And we have JFI papers also coming up.
Okay.
Thank you.
That's great.
Sorry about that.